Hi everyone! In this episode I would like to have a look at this Fluke 97 ScopeMeter, and in particular what kind of battery I can use instead of the original one. I got this unit recently from eBay for about $100, which is not much at all for such an instrument, but it was sold with no accessories at all, no probes, no power supply and no battery pack. Just this unit you see and nothing else. The model is quite old. It was produced by Philips for Fluke in early 90s, around 1992 I believe, so perhaps this unit is about 25 years old or something like that. But it still runs and can be very handy away from a lab or in a lab if you need an isolated instrument to work, for example, on some sections of a switch and power supply. So you need an instrument which is not ground referenced. This thing can run from a wide range of DC voltages, from 8 to 20 volts, which can be very handy. For example, it can run from a car battery or something like that. But there is a couple of difficulties. One is that the power connector here is recessed down a narrow hole quite a bit. Let's see. This is just to reach the tip of the center pin, which makes it a bit tricky to find a suitable connector. And another difficulty is that the center pin is negative, which limits the choice of power supplies. Of course, I can easily find a Fluke power supply specifically made for this unit on eBay or something like that. But I have tons of power supplies around the lab, so I found this 19-volt supply from an old HP laptop, which is a massive overkill. This thing can give more than 3 amps, and the ScopeMeter needs only about 200 milliamps. But anyway, I have a few of them sitting around gathering dust, so why not? But the connector is wrong, of course, and the polarity of the connector is wrong. So I found this piece of wire in my collection of wires and connectors from old power supplies, and this connector fits this unit. And I also found a connector like this, which fits the HP power supply connector, and for now I joined them like so. Later on I might tidy this up, but for now it should be fine. So now I can power this thing up. Now I need some probes, and I happen to have this pair of inexpensive probes. Model is P6200, 200 MHz, which is an overkill again. The scope is only 50 MHz, but I have them anyway, and they were quite cheap. I bought them a few years back for about $20 or $25 a pair, I don't remember exactly, and they work fine. Sometimes if pushed all the way onto these connectors they cannot be locked, but then pull back just a tiny bit and they lock fine. And pay attention, these probes have plastic insulated BNC connectors, which is important in this particular case because this is an isolated instrument, and depending on the circuit you are probing, this point might be hundreds of volts above the ground, so having an exposed piece of metal here would be very dangerous. This is the back of the unit. There you go, Philips brand. I already unscrewed these 2 screws, so let's lift the cover, which is quite tight because of this rubber seal. Let's see, perhaps you can see this the unit was designed to run on 4 primary cells like this, of size C, or on a nickel-cadmium rechargeable pack, which consists of 4 cells of the same size, and the pack has an additional contact touching this charging contact here. I have seen replacement nickel-cadmium packs on eBay for about $20 to $30, but I don't really want to buy an old technology pack. I have seen nickel metal hydride packs as well, which are probably better because they don't have memory effect and probably twice the capacity of the nickel cadmium pack. But I'm not sure it's a good idea either. In particular, because I looked in the service manual and measured myself. This charging voltage here is 8 volts. I am not sure why it is so high. These cells, nickel cadmium and nickel metal hydride, should be charged to about 1.4 volts per cell, which means 5.6 total. So why Fluke uses 8 volts here to charge, I'm not sure. And I guess that nickel cadmium pack does not care much, but I'm not sure nickel metal hydride pack can handle this abuse. Perhaps it can, because the packs are made and people buy them and they don't fail, at least right away. But I don't really want to buy any pack at all, because I think I might be able to replace it for free with what I have in the lab and have some fun in the process. I have a lot of lithium-ion cells salvaged from laptop battery packs and such, so I would like to find out if I can use a lithium-ion pack in this unit. Here is the battery charger section in the service manual, and we have some description here and this block diagram. The manual has full schematics as well, but for now let's have a look at this block diagram. This is the input, 8 to 20 volts. Then we have some sort of a filter and then a detector to let the microcontroller know that the unit is running from an external source, so that some indicator on the screen changes and the automatic shut off after some period of inactivity is disabled. Next we have this DC to DC converter, which converts this input voltage into a fixed voltage, which is 8 volts, which is used to charge the battery pack and to run the unit if it is turned on. This is the current limiting for charging the pack, and this charge protection is to connect the battery only when needed. Next we have more details about each block. This is the DC to DC converter, and here we have more details about the current limiter. And I see that when the unit is off, the charging current is 170 milliamps, and when the unit is on, the current drops to 100 milliamps. And I'm not quite happy about this low charging current. It means that the battery pack will be charged very slowly. And here we have the next section about the power supply. The input to this supply is either from the battery or 8 volts from the first DC to DC converter. This is, they call the second converter. And the voltage from the battery is not really 5 volts. I believe they called it 5 volts for simplicity here. The nominal voltage on the nickel-cadmium pack is 4.8, and the maximum when fully charged is 5.6 or something like that. But anyway, this input, either 5 volts or 8 volts, is converted into 3 output rails. And here we have an under-voltage protection, which, as I understand, works by detecting a drop on the 5 volt output rail. So the unit shuts off, not because the battery reaches a particular voltage, but because the input power is not sufficient to sustain the operation of this DC to DC converter anymore. And I believe this is very good. And this makes me think that it's gonna be quite easy to use a lithium battery pack here. Here is my idea and a greatly simplified diagram. This is the first converter providing 8 volts. It is negative and the ground is positive in this unit, but it does not matter. The second converter does not really care what voltage is here. It can certainly run from 5 to 8 volts. So suppose we connect a lithium-ion pack composed of 2 cells. The nominal voltage would be 7.4 and the maximum charging 8.4. It will not be reached, so some capacity will be lost, and we can measure how much exactly. And the minimum cutoff voltage should be from 4 to 6 volts. Different manufacturers specify different cutoff voltages. I have seen 2 volts per cell, and 2.5, 2.7 and 3 volts. And this might not be very important in this case, because the cutoff is based on not having enough power to run the second converter, not on a particular voltage threshold. We will experiment and see what happens, and I believe this should work without any modifications. Ideally, it would be great to modify the first converter slightly to increase the voltage to 8.4 to fully charge the pack. And also it would be great to increase the charging current to charge faster. But we don't have to do that. This should work as it is. Not perfectly, but should work. First of all, I wanted to find out how much capacity we are going to lose by charging to 8 volts, not to 8.4. So I ran some experiments using my lab supply as a charger and this electronic load to discharge. And I described many times in previous videos how I go about measuring, so I'm not going to waste time here. I grabbed this pair of cells from an old laptop pack. The cells are probably 10 years old or something like that. I don't remember exactly. These are Sony cells, and I believe the nominal capacity is 2150 milliamp hours. So I discharged them to 3 volts at 200 milliamps. And from full charge to 8.4 volts, I measured 1960 milliamp hours, which is about 91% of nominal, not too bad for very old cells. And from 8 volts, I measured 1500 milliamp hours, which is about 77% of this. So if this is full, this is 77%. So we are losing about 23%. Because of charging to 8 volts, not to 8.4. Here I connected these 2 cells to the ScopeMeter using these grabbers for now to experiment. Let's see if I can turn it around without losing the connections and power it up. And there you go, no problem. We can use the recording feature here to defeat the automatic shutoff. In this mode, the ScopeMeter will run until the battery dies. So I'm going to charge the pack using the ScopeMeter, discharge it, and monitor the voltage using this bench meter, which is connected to my computer through GPIB. I'm going to collect all the data and we will have a look. My experiments took quite a while. Here we have all the data. Let's have a look. This is the charging process from a fully discharged state, about 6 volts. And the voltage reached 8 volts in about, let's call it, 24 hours. But I did not stop there. I wanted to see what happens if I keep the ScopeMeter plugged in. So I waited for about 150 hours, which is a bit more than 6 days, and then I gave up. And the voltage kept going up and up and up, very slowly, but never stopped going up, and reached 8.08 volts. So perhaps some sort of a battery management module would be a good idea to use to prevent overcharging in case the ScopeMeter is plugged in for a very long time. Next, from this state, I fully discharged the pack and the runtime was slightly less than 5.5 hours. I enlarged this portion of the graph here to have a closer look. And the minimum point here was, let's call it 4.4 volts. Perhaps this is a bit too aggressive, but maybe not. Maybe this is an optimal use of the battery capacity. And I don't think this is a problem as it is, because when unit finally shut down, the voltage recovered very quickly above 6 volts or 3 volts per cell. And if we used some sort of a battery management module, that thing would cut off sooner, let's say at 6 volts here, so we would lose about 0.1 hours or about 6 minutes of runtime. And next I ran one more cycle. This time I charged for about a day, just to 8 volts, and this time the meter ran slightly less, just a bit more than 5 hours. So all this looks good and confirms that this is a working solution. Not perfect, but nothing is perfect anyway. I ordered a battery management module on eBay for just under $3 delivered. And while I was running the experiments, the module has arrived. Here it is, a nice little module for 2 cell packs. And the problem with such modules from China is that quite often documentation is poor and the resellers don't really know what they are selling. So in this particular case, what I don't like is that this model on the document does not match the model on the board. So I'm not entirely sure that these are the right specs. Let's assume they are. The module supports up to 4 amps continuous current, which is a bit of an overkill for this application. And the essential features we want are the overcharge protection set at 4.29 volts per cell and over discharge protection set at 3 volts per cell. There is also a nice little feature to balance the cells during the charging. If one cell goes stronger than the other, this module can compensate up to 70 milliamps, and this feature can extend the lifetime of the pack quite a bit. But I'm not sure it's gonna work in this case, because we are not going to charge the battery all the way to 8.4, and perhaps this feature works closer to the end of charge. We also have overcurrent and short circuit protection. Overcurrent is set way too high, at 16 amps. And for this application I would prefer this to be much lower. Let's say 1 or 2 amps would be enough. But it's hard to find a module matching the application perfectly. I would also suggest using a thermal fuse, just in case the pack overheats for some reason. It can be placed somewhere between the cells, and if the temperature goes higher than the melting point of this fuse, it just opens the circuit. This particular fuse melts at around 115 degrees C. I just happen to have a few, and this is fine for this application. Now let's see how can we physically fit a new pack in there. Unfortunately, 2 standard cells won't use the available space very efficiently, and 4 cells will not fit in there. But this is certainly the easiest way, because such cells are readily available everywhere. And I'm tempted to take the unit apart and drill a hole somewhere in the corner to pass wires, because I don't really want to ruin the contacts by soldering to them. Maybe I will never use them again, but I don't quite like the idea of damaging them. Another way is to use lithium polymer cells, which come in all sorts of sizes and shapes. For example, I had a couple of old MacBook Pro packs gathering dust for a few years. So I took one apart, here it is, and it seems like these cells can fit in there without this battery management module, of course. It seems like it fits perfectly, and perhaps even 4 cells can be squeezed in there in 2 parallel 2 series configuration, and that would be a very long runtime pack. I took this pack completely apart. It had 6 cells arranged in 3 pairs in series. So I took 2 such pairs and built this pack. Here we have battery management module, and this is thermal fuse. And this pack fits into the meter perfectly. These are Sanyo cells, this is the model. And I could not find datasheet for them, just a couple of mentionings in forums. In one forum I saw 2700 mAh, in another forum 2800. So I measured myself, again 2-3 volts per cell at 200 milliamps. And I measured this configuration, 2 series, 2 parallel. So from 8.4 volts I measured 5030 milliamp hours, which means about 2500 per cell, and this is about 92% of the nominal, if this is nominal. Not bad at all for old cells. And from 8 volts I measured 3230, which is about 64% of this. So we have more drop here when we charged to 8 volts as opposed to 8.4. In this case we only had 23% drop. But anyway, this capacity is more than twice this, and this gave us about 5 hours runtime, slightly more. And this must be more than 10 hours. Not bad at all for this easy upgrade. And perhaps one day I will try to figure out how to increase the charging voltage to 8.4 volts, and perhaps even how to increase the current to charge faster. Here I opened this thing up. I am thinking about drilling a little hole somewhere over here, perhaps in the corner, to pass this wire with this connector for the battery pack. And I need to solder to these 3 contacts. Here we are, a little hole here, a knot for strain relief. Everything is soldered. and I have 3 wires because I want to connect the charging to the positive of the battery only in the battery connector. This way I can remove the pack and still run on those primary cells if I want to. Here we are, running on the lithium-ion pack. As usually, I really hope it was interesting and useful. If you like it, give it thumbs up. Thank you very much. Bye.